Hi there, I'm happy to present our work, Instance Tracking in 3D Scenes from Egocentric Videos. Let's begin the presentation with the motivation of our work. The envisioned application of our project is the Task Assistive Agent running on AR/VR devices. As shown in the figure above, when users wear the headset and walk in the surrounding environment, they can start tracking object instances and ask the agent to help them recall the last known location of enrolled object instances. Going over our contributions, first, we develop new benchmark protocols, including instance enrollments and evaluation protocols. Second, we collect and annotate a new benchmark dataset, including raw videos, object instance collections, and annotations. Lastly, we implement and evaluate state-of-the-art single object tracking methods. Here, we visually illustrate our benchmark task. Given a video sequence and enrolled instances, the model keeps track of the 3D location of the object instance in a predefined world coordinate system. By tracking in 3D, we leverage the important prior information. An object should remain stationary unless being interacted with. This slide visualizes the raw videos in the benchmark dataset. In each video, the user performs daily activities and the video is captured by HoloLens 2. Our dataset contains 50 videos with an average length of over 5 minutes. We collect videos in 10 different indoor scenes with natural camera trajectories. Here, we describe how we enroll instances in the benchmark task. Specifically, we introduce 2 different real-world application-motivated enrollment methods. The first one is single-view online enrollment. In this case, the object instance is enrolled on the fly by the user, such as interacting or pinpointing. This enrollment type provides in-context information. However, the visual quality is lower in resolution. The second type is multi-view pre-enrollment. In this case, the object instance is pre-enrolled with a collection of images for the object of interest before the tracking system starts. This enrollment type comes with rich visual information, but images are not captured in the tracking environment. The benchmark dataset comes with 3 types of annotations. The first one is the Object Instance 3D Center. This annotation describes the 3D position of the object instance in the world coordinate frame. The second type of annotation is the 2D axis-aligned emodal bounding box. The last type is the Object Motion State annotation. This is a binary annotation, indicating either the object instance is stationary or dynamic. Dynamic state means the object is being interacted with users in the current frame. To approach the benchmark problem, we propose a novel method leveraging the unique perspective of egocentric videos and the recent powerful foundation models. In the egocentric videos, we find object instances are mostly static while the camera is constantly moving. Based on this observation, we find it is better to formulate the tracking problem in a predefined world coordinate, leveraging the important prior information mentioned before. The object should remain stationary unless being interacted with the users. Our proposed approach follows the tracking by detection pipeline. Specifically, we utilize the recent foundation models SAM and Dino V2. SAM is a powerful proposal generator. We match Dino V2 encoded features with cosine similarity for data association. In this slide, we present the evaluation protocols before showing the experimental results. The first evaluation protocol is the 3D threshold-aware precision and recall. As illustrated in the figure on the right, a true positive is counted when the distance between the prediction and ground truth is smaller or equal to the threshold. The final precision is computed as true positives divided by all positive predictions. Recall is defined as true positives over true positives plus false negatives. We also adopt L2 distance and angular error metrics introduced in the prior work. Note these metrics require both ground truth and prediction to compute. In this slide, we present the experiment results, comparing against state-of-the-art single-object trackers. Specifically, we evaluate short-term and long-term trackers. We also include trackers that use depth maps and fine-tuned on egocentric videos. The results are plotted and shown in the bar chart on the right. Our proposed approach outperforms all other trackers under both settings, demonstrating the strong performance of our model. We show the qualitative visualizations in this slide. The different thresholds are represented by different concentric circles. In other words, for each prediction, the closer to the center of the circles means it is closer to the ground truth position. We find our approach is consistently closer to the center compared to other methods. In conclusion, we propose a novel benchmark problem to study the problem of tracking object instances in 3D from egocentric videos. We repurpose and evaluate state-of-the-art approaches and develop a strong baseline leveraging foundation models. Future work should address the problem of accurately detecting object 3D motion changes and also better utilization of object instance information. Feel free to check our project GitHub page, and thank you for watching.